Okay, the next section is section, what is 1410, standing waves in air columns. And I've got a little demo here. What I was doing, I was blowing into the straw and lowering my thermos here so that the length of the available air column was varying. And what was happening is, as I was blowing over the straw, the resonance that was allowed in the straw was being selected out. I'm just blowing. I'm not whistling. I'm just blowing over the straw, but the length of the straw selects out the frequency that it's going to resonate at, and that's what we're going to talk about. We're talking about standing waves in air columns. So let's go to the PowerPoint demonstration and look at resonance in air columns. Standing longitudinal waves can be set up in a tube of air, for example, an organ pipe, as a result of interference between sound waves traveling in opposite directions. The relationship between the incident wave and the reflected wave depends on whether the reflected end of the tube is open or closed. A portion of the sound wave is reflected back into the tube even at an open end. If one end is closed, a node must exist at that end because the movement of the air is restricted. If the end is open, the elements of air have complete freedom of motion and an antinode exists. The figure shows the first three nodes of vibration of a pipe open at both ends. The first three modes of vibration of a pipe open at both ends. When air is directed against an edge at the left, longitudinal standing waves are formed and the pipe vibrates at its natural frequencies. Note that from end to end, the pattern is antinode, node, antinode, or ANA. The same pattern as in the vibrating string, except node and antinode have exchanged positions. As before, an antinode and its adjacent nodes, AN, represent a quarter wavelength, and there are two AN and NA. So let's find the wavelength and fundamental frequency. Okay. The next harmonic has an extra node and antinode between the ends, creating the pattern AN-A-N-A. Let's count the pairs, AN and A, AN and NA, making four segments, each with a quarter wavelength. We can do the same for the third harmonic. All higher harmonics, it turns out, are positive integer multiples of the fundamental. I hope that's not interfered with. Where V is the speed of sound in air. Let me read that again. All higher harmonics, it turns out, are positive integer multiples of the fundamental, where V is the speed of sound in air. And as you know, that's going to vary with temperature. Okay. Let's look at some more standing waves. Let's look at a pipe. Now let's look at a pipe that is open at one end and closed at the other, as in the figure on the left. The open end is an antinode and the closed end is a node. Here, the fundamental frequency consists of a single antinode node pair, AN. So we can calculate the wavelength. The first overtone has another node, an antinode between the open end and the closed end, making the pattern AN, AN, as shown in the figure on the right. There are three antinode node segments in this pattern, AN and A and AN. So let's calculate the wavelength. Okay. In contrast to the pipe open at both ends, there are no even multiples of the fundamental harmonic. In the odd harmonics for a pipe open at one end only are given by the relationship shown. And we're going to do this in the experiment tomorrow on air column resonance. Okay. And the next section we're going to cover is beats, and that's going to be a single slide presentation.